right, we're going to go ahead and go through 1.5. Our notes really quickly. This should be a review for you guys on electron configuration. So most of it I'll be able to go through fairly quickly. You guys have this section in your notes. Go ahead and make sure you're filling it in as we go through. So quick review on atomic structure. I'm just going to go through this quickly. Protons, neutrons are in the nucleus. That makes your nucleus positively charged. Okay, that's something that's important to remember because that's where your protons are. That makes your nucleus also positive. Electrons are negatively charged. They're located in energy levels. So when we talk about electron configuration today, we're going to talk about where those electrons are, what energy levels they're in, how they're arranged in the atom, and the reason why that's important is because it's going to help us when we talk about chemical bonding and other properties of elements has to do with their arrangement of electrons. And so that's why we need to make sure that we understand this. So this is probably a new thing for you. This is not something that we talk about usually in our first year chemistry classes, but it is a huge, huge deal on the AP exam, you guys, like huge. And so anytime they talk about periodic trends, which we're going to talk about in this unit, atomic properties, size, ionization energy, electronegativity, all of those things, they expect you to be understanding the concept behind all of those patterns and properties. And it all comes back to what is called Coulomb's law. And so a lot of times you guys are going to be answering questions and it's going to say, give your explanation in terms of Coulomb's law. And so it's really, really important that you understand this. Yes, there is an equation for Coulomb's law. It's right here. The equation is not so much important. They don't give it to you on the formula sheet. They don't expect you to do any calculations with it, but just seeing the equation can help you understand the relationships that we're going to talk about. So obviously you guys know opposite charges attract. Okay, so that means like our protons and our electrons, positively charged protons, negatively charged electrons, they attract each other. Like charges repel. That means if you have two electrons next to each other, they repel and they want to be as far away from each other as they can. That's important. The other thing that's important is to know that that force, this force right here, represents either the force of attraction or repulsion. So we're going to talk about Coulomb's law in terms of protons and electrons within one atom, and also in terms of different ions that attract each other and that strength or that force of attraction between those. So the force is directly proportional to the charge and inversely proportional to the distance between the charges. So here's what that means. As charges get closer together, the force of attraction or repulsion is stronger. So if they're opposite charges and we bring them closer together, that force of attraction is going to be stronger. If they're the same charge, two negative charges, the closer we bring them together, the more they're going to want to repel each other. And then the greater the charges are, the stronger the force of attraction is going to be. So that means like if we're talking about ions, if I have like a ion with a positive 2 charge and an ion with a negative 2 charge, that force of attraction between them is going to be stronger than if I have an ion that's +1 and an ion that's -1. That's going to have a stronger force of attraction here because their charges are larger. Okay. All right, now let's go ahead and get into our electron configuration. Okay, you guys need to know that yes, electrons are found in energy levels, but there's more to that than just energy levels. Energy levels have sublevels and orbitals within those main energy levels where they're located. And so we have to know where those are, okay? Now, principal quantum numbers is just the main energy level number. That's these right here. energy level number 1, energy level number 2, 3, 4, and so on, down to like 7, okay? And then every energy level has sublevels, and it has a different number of sublevels depending on what energy level it is. So energy level number 1 has an S sublevel. Energy level number 2 has S and P. They all have different shapes, by the way, these sublevels, and hold different numbers of electrons, right? Energy level 3 has S, P, and D. Energy level 4 has S, P, D, and F. So some things to remember, if we go to the next page, is that each sublevel, those S, P, D, and F sublevels, they have what are called orbitals. And those orbitals can hold 2 electrons each. Okay, so S sublevels have 1 orbital, and that 1 orbital can hold 2 electrons. P sublevels have 3 orbitals and at 2 electrons each. That means S can hold, P can hold 6 electrons. Our D orbitals, D sublevels have 5 orbitals, 2 electrons each. That's 10 total electrons. And then with 2 electrons for each orbital in our F sublevel, that is 14 electrons. So each of our orbitals can hold 2 electrons. Okay, other things to remember, electrons spin, okay? Now, when we do electron orbital diagrams, we draw arrows to represent electrons. We usually draw either lines, like you guys see right down here, lines to represent our orbitals, and then we put arrows in there. And if there are 2 electrons in an orbital, we draw them as arrows, and those arrows face in opposite directions. Those opposite directions represent the fact that those electrons have opposite spin directions. So the reason why that's important is because if you have 2 electrons, this electron is negatively charged, this electron is negatively charged, right? So really, they would repel each other, except for the fact that they're spinning in opposite directions. And since they spin in opposite directions, that affects their magnetic field. Those 2 things are related. You will talk a lot about that in physics. It's kind of complicated, but all you need to know at this point is that those 2 things are related to each other. And since they're spinning in opposite directions, their magnetic fields are opposite. So that allows them to actually hang out in the same orbital without repelling each other too strongly. Okay, our Aufbau principle and periodic table, this is what we're going to be using to fill up the energy levels. There's a certain order that they fill up in, and for the most part, especially at the beginning, they fill up in order. So the lower energy levels fill up first, so that's 1s first, then 2s, then 2p, 3s, 3p. Now here's right after 3p is when things start to overlap. And because there's overlapping of orbitals, then things start to fill up out of order. And so instead of trying to memorize, like you would think that, okay, 3 also has a D sublevel, so you would think that that would fill up before anything filled up in the 4th energy level. That's not true. 4s fills up before 3d because it's easier for electrons to go there because of the overlapping of orbitals. So instead of trying to like memorize the order that electrons fill up in, we're going to use our periodic table as a shortcut to help us do electron configuration. And you guys should have learned this last year, and hopefully you remember it. It's not super hard, so just going through this should be a quick refresher of your memory here. So let's see, let's talk about nitrogen just really quickly, and then we'll do some that are farther. Okay, first thing you have to figure out is you have to figure out how many electrons there are, right? So nitrogen has 7 electrons. So that means that the first energy level has an S sublevel and it can hold 2 electrons. So we're going to write 1s2 to show that there are 2 electrons there. Then the next energy level that can hold electrons. So this energy level is full, can't hold any more. So now I'm going to go to energy level number 2. The first sublevel to fill in is S. it can hold 2 electrons because it has 1 orbital. So now I have 1s2, 2s2, that's 4 total electrons. I need to get to 7. So I need to keep going. And so my next sublevel to fill up, I filled up 1s, I filled up 2s, now I'm going to fill up 2p. Now I've got 4 electrons here, so I need 7 total, so I only need 3 electrons in that energy level. So my electron configuration is 1s2, 2s2, 2p3. When I draw the orbital diagram, here's what it's going to look like. 1s is going to have 2 electrons. 2s is going to have 2 electrons. 2p has 3 orbitals, so I need to draw 3 lines to represent each of those orbitals. So this rule is important. Electrons spread out to have the maximum number of unpaired electrons. So that means that I'm going to put 1 electron in each orbital before I can pair them up. So I have to do 1, 2, 3, and then if there was a 4th one, then it would come down here and fill up and pair up with this electron. The reason why that's important is because this has 3 unpaired electrons, and that becomes important when we talk about chemical bonds. So we need to be able to figure out how many unpaired electrons there are, and in order to do that, we need to draw our orbital diagrams correctly. Okay, let's go here. So just a quick reminder for you guys that your periodic table is a shortcut for electron configurations, okay? A reminder that everything over here is your S block of elements, meaning they all have electron configurations that end in S. Every row represents a different energy level, 1, 2, 3, 4, 5, 6, 7. We've got our P block over here, and then our transition metals are our D block. So I'm gonna pick, what am I gonna pick? I'm not going to do all of these, but let's pick iron. Okay, iron. First thing you want to do when you guys are doing this, you just want to find where it is on the periodic table. So iron is right here. Okay, and if you have your periodic table in front of you, you should be able to see where iron is. Now, when you're using your periodic table to write electron configurations, you are going to start in the top left corner, and you're going to go across every single row, and it's going to help you figure out the order that your electrons fill up in until you get to iron, and then you're done. Okay, so the first energy level that fills up is 1s. 1s has 1, 2 electrons in it, so I'm going to write 1s2. Next thing to fill up is 2s2. Then after 2s, I have 2p that fills up, so 2p6, and if you count across 1, 2, 3, 4, 5, 6, it even tells you how many electrons are going to go in that sublevel. Then from 2p, I go to 3s, that holds 2, then I'm going to have 3p6, and then I'm going to have, this is where when you go to the next row, you don't have to memorize that 4s comes next, you just use your periodic table as a shortcut to figure that out. So I have 4s2, and then this is 3d. So 3d, and then I'm just going to count across 1, 2, 3, 4, 5, 6, 3d6. This is the long electron configuration for iron. But there's a shortcut, right? The shortcut is to look at the noble gas that comes before the element that you're writing the electron configuration for. So the noble gas that comes before iron is argon. So instead of having to write all of this, I can just go ahead and write argon in brackets. And then from there, after argon, the next thing to fill up is 4s2. And then 3d6. So this is my electron configuration. You can always write it this way unless they tell you specifically for the full or complete electron configuration. Other things that are important to know, valence electrons. Valence electrons are the ones that are in the energy level that has the highest number. Okay, so that's the big number in front, the 1, 2, 3s, and 4s. So these are my valence electrons. They're not necessarily the ones that I filled up last. It's the ones that are in the highest energy level number. So there are 2 valence electrons for iron. That's important for charges and bonding and all of that as well. Okay, so here's what I want you guys to go ahead and do. I want you guys to write electron. Let's not do uranium. We'll come back and do that. They don't usually give you these ones down here. Go ahead and write down, or take some time, pause the video right now, and write out the electron configurations for sodium, sulfur, iodine, and gold. And then when we come back to class, we're going to go ahead and go over those and make sure that you guys are good with writing electron configurations. All right, we're almost there for our notes for today. Go ahead and turn to the next page. We're going to talk about electron configurations of ions. Okay, so just a reminder of what an ion is. An ion is any atom that has either gained or lost electrons, and so it has a charge. Metals lose electrons and become positive. Nonmetals gain electrons and then they become negative. So let's take a look at what that looks like. Okay, let's talk about the calcium ion, calcium 2+. I don't have my periodic table. That's not helpful. Okay, you guys have your periodic table in front of you. Find calcium. Okay, what you're going to do is you're going to start with the electron configuration of calcium, the atom. So if I write out the atomic electron configuration without gaining or losing electrons, it would be 1s2, 2s2, 2p6, 3s2, 3p6, and then 4s2. Because it has a +2 charge, it's losing 2 electrons, and it loses its valence electrons. So those go away, and this becomes my electron configuration for calcium. Unfortunately, you cannot just write that as argon. Okay, they don't like that very much. You can write it as neon 3s2, 3p6. They always want like that last part, that last row written out and not included as part of your noble gas brackets. Okay, let's talk about sulfur real quick. Sulfur is -2, and we know that because it's in the same row as oxygen. It gains 2 electrons to complete its octet, right? It's got 6 valence electrons and it gains 2 more. So let's talk about the normal electron configuration for sulfur would be neon and then 3s2, 3p4. This would be the sulfur atom. But since it has a -2 charge, that means it gains 2 electrons, and so this 4 becomes a 6. That's going to be my electron configuration for the sulfur ion. And no, you cannot write argon for that either. All right, let's talk about iron. We did iron, right? Yes, we did. So going back to iron, just the iron atom was argon 4s2, 3d6. Okay, this is tricky and it always messes people up, but it's like on the AP test a lot, so really make sure you understand this. Transition metals, they lose their valence electrons first. We talked about which ones were the valence electrons. They're the one in the highest energy level, right? So it has a +3 charge, so it has to lose 3 electrons. The first electrons that it's going to lose are the valence electrons in the highest energy level number. So those 4s electrons, they go away. And then there's still one more that has to be taken away. So that 6 is going to turn into a 5. Biggest mistake here is that people want to take 3 away from here and say 4s2, 3d3. That's not right. You have to lose the valence electrons first, and then if you still have more that have to be taken away, then you can take it away from what's left over. Okay, so argon 3d5 is actually our electron configuration for the iron 3+ ion. Okay, go ahead and pause the video and work through those ion electron configurations right now. Okay, we're going to go over those in class also. So let's talk about ionization energy and Coulomb's law. So reminder of ionization energy is the energy required to remove an electron from an atom. So that's going to be important for us to understand what that is, the definition, and also the explanation of why certain elements have greater ionization energy than others. So that's important. Anytime you're asked to write the general formula for ionization energy, you're always going to show the element, the electron being removed, and if an electron is removed, that makes the ion positive. Okay, let's see, first ionization energies. There are multiple ionization energies for each element because they have multiple electrons. The first ionization energy is how much energy is required to remove the highest energy electron, so that first valence electron. And then once that one is gone, then the energy needed to remove the second electron is the second ionization energy. The second ionization energy is always greater than the first ionization energy, always. Because as you remove electrons, when one electron gets removed, then the atom shrinks a little bit. And since the atom shrinks a little bit, those next electrons are closer to the nucleus. And if we remember what we talked about at the very beginning of our notes today with Coulomb's law, the closer they are together, the stronger that force of attraction is. And so since that second electron is closer to the nucleus, it's going to have a stronger force of attraction, and so it's going to be harder to pull away. And so you are going to be asked to definitely use this as an explanation when we're talking about ionization energies. The closer the electrons are to the nucleus, the harder they are to remove, and that makes the ionization energy greater. All right, we're going to go ahead and stop there, you guys, today. Bring this back with you to class, and we're going to do some electron configuration practice, talk more about periodic trends and ionization energy and some other things in class. So I will see you guys in class.